In this video, we're going to talk about physical and chemical changes. At this point in the year, identifying chemical changes tends to be a little bit harder because we don't really know enough chemistry to truly work with the different chemical reactions. However, we can still manage to do it if we focus on the keywords that identify chemical changes. So let's go over what they are. In a physical change, the material's identity does not change. So in other words, you still have the same stuff you started with, it just may be in a different form or a different phase. Some examples are any phase change. So if you boil water into steam, it's still H2O. If I melt an ice cube into liquid water, it's still H2O. So the identity of the material as H2O hasn't changed, just its phase has. If I take a rock and crack it in half, it's still a rock, it's just broken in half. If I go a step further and grind it up into dust, those dust particles are still the same material that made up the rock, they're just in a different form. If I crack an egg, notice I'm saying cracking, not cooking. If I crack an egg, the eggshell, for example, it's the same material, now it's just broken, okay? It's like if I broke a piece of glass. The glass is still glass, it's just not in its original form. Now, chemical changes are changes that do change the identity of the material. So typically what's happening is the element or compounds that make up the material are going to change into different elements or different compounds or combinations of them. So an example would be burning wood. The wood itself, once it's burned, it's changed into different things. When you burn wood, what's left? Well, the wood essentially disappears. That's not really true. It turns into gas and heat and some of the ash and charcoal that is left over when you're done burning the wood. So you can't really unburn that. Now, we say the word spontaneous production of gas. First thing I want to review is the word spontaneous. So when something is spontaneous, it just happens unexplainably. So if you trip, that's spontaneous. If you intentionally trip, then that obviously isn't really a trip as what we would explain it. So spontaneous, the best way to describe it in chemistry is by saying it is an unexplainable happening, right? So when we say production of gas, we are really saying an unexplainable production of gas, or maybe a not obvious or not a non-phase derived change. So an example would be if I mix Alka-Seltzer and water, I get that fizzing. Well, that fizzing is gas. That is a spontaneous production of gas. I didn't turn the temperature up of the water and boil the water to produce the gas. The chemicals in the Alka-Seltzer mixed with the water produced the gas on their own. I didn't do anything. We call that spontaneous production of gas. Spontaneous color change. What this means is I mixed clear and clear and got something other than clear. Or I mixed red and red and got something other than red. Not I mixed red and yellow and got orange. That's just you mixing colors. If you mix a red liquid with an orange liquid, with a yellow liquid, and they don't turn orange, well then that would be an unexplainable color change. Formation of a solid. Not I put something in the freezer and it turned into a solid because it froze. That's explainable. That's a phase change. I mean, I mixed two things together that weren't solids and they became a solid without me changing the temperature. Production of hot or cold. Not I put something in the microwave, the stove, or the oven, or the freezer, meaning I mixed two things together and they got hot or cold on their own without me adding heat. So that's what we mean by spontaneous. Examples of spontaneous hot or cold are the classical hot packs, not the ones you have to put, and cold packs, not the ones that you have to put in the microwave or the ones that you have to put in the freezer, but the ones where you crack the little thing inside of them, you shake them up, and the chemicals inside mix, and then they get hot or cold on their own. Those are chemical changes. So keywords for identifying chemical and physical changes. We'll start with chemical. There's less of them. So burning, oxidizing, combustion, or rust. These are all actually the same process. It's when you add oxygen to something, that's what happens. It's what actually the real difference between burning and rusting or oxidizing and combustion. There's really not much of a difference, more about speed and things like that. If you see the word reaction, like a chemical reaction, if we talk about a spontaneous color change, the word neutralization or neutralize is a chemical reaction, and so if you see this word, you're automatically going to identify it as a chemical change. Decompose or break down. Fizzing, that is spontaneous production of gas. Fizzing is another way of saying it. So these words clue you in that you're dealing with a chemical change. Now, as the year goes on, we will learn much more about the individual reactions that we're talking about, and so that will make more sense. But for right now, we're just going to identify them based off vocabulary. So for physical changes, We're talking about any phase change word. So melting, fusion, vaporization, boiling, solidification or freezing, evaporation, sublimation, deposition, condensation, any of them. Any of the words that we use to describe separation techniques. So like distilling, filtering, dissolving, and diluting. So these words are words that we use. These are things we do in a lab to separate and purify chemicals. They separate things by physical methods, not by chemical, and that's why these would all be a physical change. The word malleable and ductile, if you see these, they are going to be clues that we're talking about a physical property. Malleable just means bendable. If I take a paperclip and I bend it, did I change the identity of the metal that made up the paperclip? Of course not. If ductile means conducts electricity. If I conduct electricity through a wire or turned it into a wire even, then that's not going to change the identity of the metal that made up the wire. All right, so these are the keywords for identifying physical changes. A couple things to remember. Elements can never be decomposed, and by definition, because they are elements, they can't be broken down. Now, we will find out that you can, in fact, later on, break an element apart, but you essentially destroy it, and it's not that element anymore, which is why we say they can never be decomposed under normal means. Whereas compounds can be broken down, and they can even be put back together after they're broken apart. And so compounds can be decomposed. A couple more vocab words, and then we'll do some practice problems. So intensive versus extensive properties. Intensive properties are physical properties that do not depend on the size of the sample. For example, density, color, ductility, or malleability. So what that means is if I have a little cube of metal, like we use in some of our labs, that density is going to have the same, the density for that cube would be the same whether I had a little tiny cube or a really big cube of the same material. The density would be the same. The size and mass and volume will be different, but when I calculate density specifically, I'll get the same density. And that's really the difference between extensive and intensive. Color, a little cube of silver will be the same color as a big cube of silver. Ductility, a little cube of silver could be pulled into or conduct electricity the same way a big one could. Malleability, a little cube of silver could be bent or hammered into sheets or made into wire the same way that a big one would. The only difference is the little one wouldn't make as much because it's smaller. Extensive properties, properties that do depend on size. Example, mass and volume. This is easy. Big cube's going to weigh more than little cube. Big cube's going to have more volume than little cube. So extensive properties do depend on the size of the sample. Intensive do not. They are intrinsic or built into the material, and so they're not going to matter how much of it you have. Here's some examples of what they are or physical and chemical changes. I have the answers on here. I'm just going to talk about them all. So Alka-Seltzer, not obviously Alka-Seltzer on its own, but when you put it in water, it fizzes. That is what we would call spontaneous production of gas. It is a chemical change. Turns out the chemicals in Alka-Seltzer only need to be dissolved into water in order to form the reaction. They won't react when solid, which is why it needs water to react. Melting ice, boiling water, making ice. They are all physical changes. We find all of those things, right? Fusion, solidification, and vaporization. We find them all on a heating cooling curve, therefore they're all physical. Cooking an egg. So if you think about what cooking is, cooking, believe it or not, is just partial burning. So if you overcook your food, most people would say, oh, you burnt it. And that's actually what happens. So when we cook things, we're just doing a controlled burn that is only cooking them partially. The only difference between that and a fire is in a fire, we want the wood to burn down completely, whereas if we were trying to cook wood, we would only heat it up to a certain degree or a certain point and prevent it from burning. We want to go to almost burnt, depending, I guess, on who you are and what your preferences are. So that's what cooking an egg is, because you can't uncook it once it's been cooked or burnt. Exercise. So exercise, we say it's a physical activity, right? But I'm not talking about that. When I say exercise, I'm talking about your metabolism that gives you the energy to do the exercise. That is a chemical process. Grinding up a piece of chalk. Well, the chalk is still chalk. It's just powdered chalk instead of a solid, stick of chalk. Rusting a nail. Rusting a nail is actually a form of oxidation, and on both rusting and oxidation is a key word, so that's how we would know that. Obviously, we'll learn these reactions in full detail much later in the year. Cutting a piece of wood. Well, if I cut up a piece of wood, I may kill the tree, but the actual wood that made the tree is still wood. It's just now cut from the main branch. So that's a physical change. Grinding that wood up into sawdust, same thing. It's just like grinding up a rock. The wood is still wood. It's instead of a single large chunk, it's now lots of little tiny pieces that we call sawdust. Photosynthesis is when a plant takes in the sun's energy to grow. That growth is a chemical change, and so it's a chemical process. And burning of wood, it's the same as cooking an egg. I went over the difference already. So burning anything, for that matter, is a chemical change. So this is just a couple examples of them. The key thing to remember is to use your keywords to figure out which ones are chemical and physical at this point in the year. And then as the year progresses, you will learn all of these fancy chemical reactions. And then this will become much, much easier because then you'll understand what these reactions are.